Let us take a break. Remember, it's a joke, don't take it to heart. But as a joke, let me introduce you to the real world of engineering and business and so on. There is a building, large building, and they want a very fancy fence around the whole building. You understand fence, right? The building is there, outside there are lawns and so on. You want a boundary wall, fences and so on and so forth. And it's a very elegant building, so this is important. So when it is announced, then 3 different companies bid for it. You see, you understand, when there is a contract, you bid for it and then you will say that this bid is good and so on. So one company is from an African country, another from Germany, a third from England. The English contractor sends a guy, technical guy, he comes here, he takes a tape measure, does all the measuring and does some calculation, and then he tells you that I think the job will be around 90,000 US dollars. 40,000 for materials, 40,000 for labor, and roughly about 10,000 as profit. So total 90,000. The German engineering around the world is very famous for their quality and so on. So they also come and they measure and this and that, calculate, and then they say that we will do it for 70,000 total. 30,000 for materials, 30,000 for my labor crew, and 10,000 for profit. So now, of course, your company is already leaning towards the German solution, that Germans are very good and they are lower than the English. But now the African contracting company comes to you. He does not do any measurements, he does not do any calculations, but you are the representative of your company. He comes to you and in a very small voice, he whispers to you, $270,000. You say, my God, this is ridiculous. What, are you joking? You did not take any measurements, you did not do any calculation, and such a high cost. He says, listen, 100,000 for you, 100,000 for me, and we will give the job at 70,000 to the German company. You will get a good job. Joke is over. We now start talking about the last part in this series. If you remember, the iron carbide diagram or the steel diagram, there are 2 very critical points, the eutectic point and the eutectoid point. The eutectoid is 0.8%. So when we were talking of below, above and so on, one thing was the temperature, that if you are above a certain temperature, you are pro and so on. So that was one thing. And on the percentage of carbon, on the concentration, on the composition line, horizontal line, there was the word eutectoid and the word hypoeutectoid, anything less than 0.8. So now this is the last thing, hypereutectoid, anything that is more than 0.8% carbon steel, right? So this will be explained in a much better way when we take an example of any hypereutectoid plain carbon steel on the diagram, which we show you on the next phase. So we are not, right? And again, we are talking about homogeneous cooling, slow cooling, so that from a high temperature, when you keep coming down, the normal changes in the phases happen, and we will discuss that, right? So eutectoid is 0.8, hypoeutectoid is any percentage less than 0.8% carbon, and hypereutectoid is any percentage of carbon more than 0.8 until you reach the eutectic. Eutectic is a totally different thing, right? Then eutectic will start. So from 0 to 0.8, it is hypoeutectoid. Exactly 0.8 is eutectoid, plain carbon steel. And then from 0.8% carbon until all the way to eutectic, you have hypereutectoid plain carbon steel.
I am showing you the full diagram. This is the eutectoid region. This is the eutectoid. So this is the hypoeutectoid region and this is the hypereutectoid region. So just to make things clear, we will blow up the diagram and show you only that we are here in this region. So that is what we see here, right? Remember, this is the eutectoid point, that was hypoeutectoid. All this is hypereutectoid. As an example, we are taking 1.2% carbon. 1.2% carbon steel, which is an example of a hypereutectoid plain carbon steel. So we just draw a vertical line. And then we see the changes as we cool from a high temperature, point A to point B to point C to point D to room temperature, right? That is what we do. And what are the four questions always? That given an initial composition and given any temperature, what are the phases present? What are the compositions of the phases? What are the mass fractions of the phases? And what is the structure diagram, right? Those are. So given 1.2% plain carbon steel at point A, what are the phases present? Only gamma, only austenite. What is the composition? The same as the original, 1.2%. What is the mass fraction? 100% gamma, there is nothing else. And what is the structure? Make a circle, make some grains, and each grain is gamma austenite, right? So this is point A. When we keep on cooling, nothing happens. When we hit the line, something changes. So just below the line, we have point B. Now this line, this solid line, what is on the left? We have gamma. What is on the right? We have cementite. So once we hit the line, what will happen? Some of the gamma will start to change into cementite. Where will it start to change? On the grain boundaries. So you see at this point, we have made the grain boundaries darker. We could have any other shade, and we are saying that this is the cementite. So on the grain boundaries, some cementite has formed. The rest remaining is still gamma austenite. You keep on cooling it until point C, but point C is still in the same region above 723 Celsius. So these grain boundary lines will become thicker and thicker and thicker, and this thicker lines will still be cementite. The rest will be gamma. But the proper name will be that here or here, this is pro-eutectoid cementite. This is cementite which is formed above the eutectoid temperature. Once you hit the line, all the remaining gamma will change into perlite, right? Because below this you have perlite, alpha plus cementite. So once you hit the line, so just below it is the point D. At point D, what has happened? Whatever pro-eutectoid cementite was there is still there, the dark lines on the grain boundaries. But whatever remaining gamma austenite was there has changed into perlite. So you give some other dash line for this perlite. So at this eutectoid line or anywhere below, even at room temperature, this is the diagram. You have the dark lines which are the pro-eutectoid cementite, and you have the dashed lines which are the eutectoid ferrite alpha and eutectoid cementite Fe3C, right? So you call it eutectoid perlite or you give them the full names. So pro-eutectoid cementite, eutectoid ferrite, eutectoid cementite. That is what you will get once you hit the eutectoid temperature of 723. And after that, if you keep on cooling further to room temperature, no more structural changes will happen, right? So if you have any hypereutectoid steel, which is any steel which is more than 0.8% carbon, then this is what will happen. Draw a vertical line on whatever composition you have. At the very high temperature, you will have point A, which is pure austenite. Once you cross the solid line, any point B will be some cementite and some gamma. If you keep on going down, more of the gamma will change into cementite. So cementite line will become thicker, but you will still have a lot of gamma. Once you hit the eutectoid temperature of 723, all the remaining gamma will change into perlite. So in the final diagram, you will have thick dark lines of pro-eutectoid cementite and alternate lines of eutectoid ferrite and eutectoid cementite, which together are known as ferrite, right? Perlite. So this is the thing that we are not doing any numerical examples on hypereutectoid because they follow exactly the same pattern as you do on the hypoeutectoid. You see, if I draw any line here, you have gamma, then you have alpha plus gamma, then you have perlite. Here you have gamma, then you have gamma plus cementite, then you have perlite. So only that here alpha will form, here cementite will form, but the other things, the calculations and so on, are just the same. So we will not do any diagram of the problem on this. And sorry, before going to a problem, what will be the microstructure under the actual microscope? So if you see there on the grain boundaries, very thick lines on the grain boundaries, very thick lines. So these are the pro-eutectoid cementite, and everywhere else is the perlite, which is those fine lines, fine alternate lines. And in the perlite, you have again cementite and you have ferrite. But in that one, the ferrite is eutectoid ferrite and the cementite is eutectoid cementite. So this is the microstructure. Once we do that, we again just do it. So I will not take a lot of time. We are doing it interactively. We have some initial composition C naught, and we are seeing at a higher temperature from gamma what changes will happen. So initial structure is shown. Then you hit the line. As soon as you hit the line, some cementite is formed on the grain boundaries. Then you go below, more cementite is formed on the grain boundaries. The grain boundaries, very thick grain boundaries of red color are there. If you cross the eutectoid temperature, then the remaining gamma is changed into perlite and the structure is the same as we see. Okay.